Hi, everyone. Thank you so much for this final session for large-scale systems, buildings, and infrastructure, transportation, and energy. I'm really happy to be here today. And it was really nice to work with my co-chair, Jeremy Gregory. It was fun to work with him on this and to meet so many talented people in this area. And I have the pleasure to introduce our first speaker, Bradley. And so the format will be Bradley and the rest of the speakers will speak for about 15 minutes, and then we'll follow up with questions. So Bradley, without further ado.
All right. Let me get this set up. Good evening, everybody. My name's Bradley, and I'm a master's student currently studying at the University of Toronto under the supervision of Dr. Shoshana Sachs. And today I'll be presenting a summary of some research that we've been conducting about construction materials that make up an urban road network through a case study of Toronto. And in this presentation, I'll be talking about, first of all, why understanding material stocks in urban transportation infrastructure is important, and also how methodological choices with respect to archetypes or typologies used to represent infrastructure components can significantly impact the findings in material flow analysis research. This research is in part motivated by the fact that construction materials represent a growing share of global greenhouse gas emissions. So as this chart shows, in the 20-year period between 1995 and 2015, global GHG emissions have increased, but GHG emissions associated with construction materials has grown faster. And this motivates the need for greater material efficiency when it comes to the built environment. But that implies that we need to establish appropriate benchmarks based on knowledge of current material stocks. However, data is typically difficult to obtain because detailed records simply don't exist or are scattered among government departments and private infrastructure owners. Nevertheless, material flow analysis is widely used to characterize the stocks and flows of resources with whatever data can be found. However, I'll note that horizontal infrastructure, for example, roads and rail, is often studied less often than vertical infrastructure like buildings. And also that archetypes, which are widely used in MFA work, can obscure real-life geographic variation. And archetypes are basically typical designs that can be used to represent components of infrastructure in order to scale estimates from components to a system or a road network or a built environment or a city, for example. In roads, for example, we might look at a particular road type and say that on average, we expect it to have around 3,000 tons of concrete and asphalt per kilometer, whereas a different road type might have around 9,000 tons per kilometer. In this project, we managed to get access to a detailed data set owned by the City of Toronto for their road network that has detailed data related to the pavement composition. And what we wanted to do in part was to compare the material stock estimates we obtained using that database with what we would obtain using archetypes. So the main research questions were how much material is embodied in Toronto's municipal road network. Secondly, how effective are pavement archetypes versus more spatially disaggregate data? How are construction materials spatially distributed? And then what material flows have supported pavement rehabilitation activities? The scope of the study covers around 5,600 kilometers of the municipal road network in Toronto, which covers about 630 square kilometers. And the city is home to almost 3 million people at this point. We estimated the stocks of asphalt, concrete, and granular material in pavement, sidewalks and curbs, as well as bridges. And I'll go into a bit more detail on that now. As I said, we wanted to use two methods, specifically looking at the pavement component of this study, The first involving archetypes, where we used typical pavement layer thicknesses combined with road surface areas from the city database in order to estimate material volumes. And then in parallel, we used more detailed, measured and as-built thicknesses from the city database to obtain material volumes that we could compare to the results using the first method. We also incorporated sidewalks and curbs because the length and type was included in the city database, which we could combine with cross-sectional areas of materials from standard design drawings in order to obtain material volumes. And finally, we incorporated a rather rough estimate of the above-ground concrete volume in bridges using scaled aerial and ground-based photos to try to develop a very rough 3D massing of the concrete components in bridges. And finally, there were maintenance activities included in the database, and so we were able to estimate maintenance flows into the pavement network. Turning first to the archetypes, I wanted to describe what those look like. These are based on the City of Toronto's structural design matrix, which is a quite prescriptive matrix of possible pavement designs based on various levels of traffic and ground conditions. And we combined or basically averaged values from that matrix across functional classes. So for example, local, collector, and minor arterial roads, and across the location or use type of the roads. So according to the city's pavement design manual, flexible pavements are preferred in suburban areas, and composite pavements combining concrete and asphalt are more common in denser urban areas. Turning now to the results, this graph sort of summarizes the main findings in terms of estimated material stocks. But though we observed quite large differences in the stocks depending on the methodological approach. So I'll draw your attention first to the blue bars. The blue hatched bars are the material stocks we estimated for each material type using the pavement archetype method. And then in solid blue is what we observed from the municipal road database. And you can see that for asphalt, the estimates were quite similar, but we observed a quite large difference when it comes to granular material, where the archetype approach greatly overestimates the quantity of granular material, whereas it underestimates the quantity of concrete. And these differences were quite surprising and quite significant. Just to put these quantities into context, looking at the volume of concrete that we estimated from the city database, around 9, and the methods that I described earlier, those volumes amounted to around 9 million cubic meters of concrete, which for people familiar with Toronto is equivalent to around 220, to the concrete embodied in around 220 CN towers, which is sort of the emblematic structure of the Toronto skyline. But as you can see, these volumes are quite significant, and so are the differences. Turning now to why we observe such differences. In part, it's due to geographic and historical differences in pavement design and construction approaches across regions of the city. So in the central core, for example, the granular layer tends to be much thinner than in other areas of the city. And the pattern that we observe in this map very closely matches the map of the former municipalities that were amalgamated to form the modern day city of Toronto more than 20 years ago. And even though these former municipalities don't exist as separate political entities, and all transportation-related construction is controlled by the broader City of Toronto, we can still see quite strong patterns in the main map that reflect these historical differences. Turning now to the third research question that we were looking at, which concerned the spatial distribution of embodied materials. Here we present the spatial distribution of what are effectively material intensities of asphalt. Material intensities are very common in this type of work and are typically normalized on a surface area basis. So kilograms or cubic meters of material per per square meter of road surface or per square meter of floor area in a building. But here we also normalize by the sum of population and jobs in each city ward, which sort of serves as a proxy measure for the typical number of users of the municipal infrastructure in each ward. And we looked at the data in this way to think a little bit more about material efficiency strategies, going back to the original motivation for this work. So I think on one hand of the material efficiency equation, we have using less, which could involve optimizing maintenance and rehabilitation strategies to reduce our consumption of material. But I also think that making better use of what we have is an equally important and equally valid approach to improving material efficiency. And the second point speaks to opportunities to better integrate land use policies with the development of transportation infrastructure. So returning to the map we were looking at previously, looking at the spatial distribution of construction materials, there's a pattern of areas of the city where large quantities of materials are embedded in the infrastructure. But on an area and population normalized basis, the infrastructure is arguably underutilized relative to other areas of the city. And I think that material efficiency is an additional argument that's relevant to this discussion around densification and planning for how the Greater Toronto Region will accommodate the millions of people that are expected to arrive over the next 25 years. So, effectively, areas where materials are potentially underutilized could be ideal locations to encourage more housing while reducing the cost of upgrading transportation infrastructure, and thereby reducing future embodied emissions as well. Now, of course, there are many other factors that are relevant to policies surrounding infrastructure provision, such as zoning rules and building codes. But in general, the higher density development in Toronto that is needed based on these population projections is quite restricted to a very limited number of designated corridors. Which leads in part to the imbalance in material intensity on a per area and population basis that we observed in this research. Finally, I'd like to briefly touch on some findings with respect to pavement input flows. So again, this was based on maintenance and rehabilitation activities that were recorded in the city's pavement database. And we calculated that over the 20-year period ending in 2017, the average annual pavement stock replacement rates were around 1.4% for asphalt and 0.3% for granular and concrete material. And for granular and concrete, those are more or less consistent with what we would expect based on the projected design lives of roads. Based again on the City of Toronto's guidelines. And asphalt is more or less consistent with what we would expect based on the rehabilitation of the upper pavement layer that occurs on every 20-year basis, for example. But that number is quite low if we also consider the reconstruction of roads that also occurs on a longer basis, but for example, 75 to 100 years. And essentially, the asphalt replacement rate was a bit lower than what we would expect, which seems to be consistent with what the city is reporting in their current budgeting projections, where currently the funding levels are only sufficient to address around 1/3 of the city's rehabilitation needs. And the repair backlog is expected to more than triple from about $1.2 billion to $4.5 billion over the next 10 years. So I think these projections are indicative of significant underinvestment in road maintenance, and material flows will eventually need to increase to catch up on this deferred maintenance and replacement. To wrap up, I think I would put my conclusions into two main categories. First of all, on the side of the industrial ecology practitioner, I think it's important to acknowledge the limitations of archetypes. I think anyone that works in this space is probably already aware of these issues, but the differences we found in this study and that colleagues have found in similar studies are sometimes quite surprising. And especially surprising for me, considering that roads can be considered to be fairly simple components of the built environment compared to buildings, for example. And here again, we're only looking at a quite limited geography. So if we're working hard to achieve gains of 5, 10, or 20% in material intensity or embodied greenhouse gas emissions, it really behooves us to do better in order to ensure that our benchmarks based on existing stocks are appropriate. And then secondly, on the policy side, I think that for municipal governments, material efficiency strategies could include prioritizing development where embodied materials and infrastructure are underutilized. And on the government side, we would also argue that governments should invest in maintaining construction material inventories themselves. And I think that the City of Toronto is particularly well positioned to do so, as they already publish a great deal of open data related to the city's built environment. And with that, I think I will end, and I'd be happy to take any questions.
Thank you so much, Bradley, and thank you for a great presentation. So I would encourage the audience, if you have any questions, to please join us on the podium, or you can type questions in the chat. I'll start off first with my first question, because I think you started to touch on this maybe a little bit at the end, Bradley. And I really have a question about equity and where investments are made. So for example, you had mentioned kind of the underutilized areas that you could look at that with the models that you've developed. Mm-hmm. And if you look at slide 11 or 14, do you think you could also use your approach to determine if funds aren't being used equitably, and really think about where investments should be made in different neighborhoods?
Yeah, I think that's very interesting, and I think that might very well be a good addition to this research, especially considering that we have disaggregate maintenance data. So, I don't really know if we would see what we would see in terms of the stocks overall, but I think it would be very interesting to evaluate, for example, if the maintenance flows, how they relate to sort of socioeconomic patterns in the city.
Yeah, so I was thinking you had like the volume, I think it was per capita maybe.
Yeah, exactly.
You also include like an income or like other kind of indices. It might be
really to normalize on a different basis.
Yeah, exactly. So that's
I think that would be a very interesting addition.
Okay, great. And I also had another question. Can you talk a little bit about how you got the data from Toronto? Sometimes it's so difficult to get data from government agencies, and kind of your strategy or the relationship that you had with them.
To be honest, this part's not that interesting because I sort of inherited this data set. So okay. My supervisor got it before I started with her. But I think it was at least a year-long process.
Yes.
And we did clear these results with them before making any moves towards publication.
Okay. And then I just have one more question. Can you talk a little bit, I know you decided to go by volume and I understand that. Can you talk a little bit about the cross sections and how they may differ across material types?
The pavement archetypes, you mean?
Yeah.
And how they would differ?
Like, so instead of doing it, I can understand why you didn't do it by mass, because obviously it would be really different. I don't know if that would be a good comparison, but can you talk a little bit about how the thickness then changed across the different types of pavements?
Yeah, I mean, the thicknesses in general are based on the traffic volumes and ground conditions, which normally in these types of studies you don't have access to, which is why we tended to group them by functional class. And then as to the question about why volume and not mass, I think, yes, putting things in terms of mass would probably enable better comparability with other studies. But in this case, at this stage, we've kept things in the original unit just to avoid adding more uncertainty with another conversion factor.
Okay.
But yes, I think putting things in mass is probably a more standard approach, at least when you're comparing different studies.
Yeah. Jeremy, did you have a question?
Yeah. Great work, Bradley. What the chart where you showed kind of the differences in the material estimates from the different approaches, and you mentioned how like archetypes in some cases was an overestimate, and it was, as you said, kind of interesting to see what the differences were. But what I wondered, and I don't think you necessarily intended this, but was like how do we know what's an underestimate or an overestimate, right? It could be they were all underestimates or something like that, right? So I don't know if you had a sense of, it's just kind of an interesting question of how you know what the correct answer is, right?
Yes, and I certainly wouldn't want to imply that the results from the maintenance database are necessarily correct either, because this has been assembled over decades, and we did, unfortunately, I don't have that graph handy, but we did do a sensitivity analysis to see, for example, setting different density cutoffs between, because that was one of the main drivers of differences in the results from the archetype approach, because we had to assume where flexible pavements versus composite pavements are used, but. Sorry, does that answer your question?
I think so. Like I said, it just kind of led me to what, when you have different approaches, how do you really get a sense of is the baseline, right? They all have their positives and negatives, right? I don't know. It's like when you do a process-based versus an EIO LCA, right? They both kind of have their positives and negatives. Saying which one is more accurate sometimes is a challenge. So it seemed like a similar challenge here as well. Right?
And I think in MFA, the problem is you usually don't have much to compare with. It's such a struggle just to get one data set that in the end of the day, it's one number that's propagated through. So this was an opportunity to try two different approaches.
Exactly. That's great. Okay, nice.
Okay, Bradley, great job and great presentation. Thank you so much. And thank you for joining us in this difficult time zone for you too.
No worries, my pleasure. Thank you.
Okay, so I think our next presenter is going to be Hessam. And so I have the pleasure to introduce Hessam, who will be next.
All right. Thank you for the introduction, Melissa, and thank you everyone for joining this presentation this late afternoon or late night. Today, I'm going to talk about the role of pavements in mitigating the U.S. climate change impacts. It's a collaborative work with my colleagues and advisors, Fangi Gu, Jeremy Gregory, and Randolph Kirchen. So to start this presentation, I'm going to talk about the American job plans that you might have heard of, that President Biden plans to increase $100 billion to modernize, or in other words, maintain or repair the roads, more than 20,000 miles of the highways and roads and main streets. And the quotes that we can see here, that is about fixing them first and fixing them probably right. But to do that, one of the main criteria that they are going to consider is the sustainability and the implications of the pavement life cycle GHG emissions. It raises these questions that we have different phases and components in our pavement life cycle, starting from materials up to the end of life. Therefore, we have different opportunities to reduce the GHG emissions of the pavement network. For example, we can have some embodied impact reductions. How much mitigation can we get from the material productions and manufacturing? Or how much we can get from the use phase more specifically. Pavements are very, pavements are covering more than 40% of the urban area, and the reflectivity, or in other words, the albedo of the pavements, can contribute to climate change impact. Or the maintenance and repair actuals, how much mitigation can we get by spending more money to maintain or make our roads smoother? And at the end of life, it's to do with the recycling factors or the end of life carbonation for example, concrete pavements that I will discuss in more detail later. So here we define the objective to investigate the role of life cycle environmental performance of US pavement network in lowering the GHG emissions. And it's a very complex question to answer because we have different road classes in the United States, starting from high volume traffic roads, very well maintained, interstates, arterials, correctors, and locals. And these roads have different levels of traffic and in different locations and different segments. And the surface condition of these roads are different. Some of them are very well maintained, so the surface is not that much rough, or there's not that much cracking over there. And some of them are under invested, therefore not enough maintenance and repair has been already applied, or they have a very rough surface. And the deterioration rate is quite different for different types of roads. Again, depending on the thickness, the traffic volume, or even the climate condition, the level of and the deterioration rate is quite different for different roads. And at the end, the maintenance and repair actions are different in different parts of the United States and different regions. There are some local adoptions of the maintenance and repair schedules that should be considered for assessing and for investigating the role of pavement life cycle. And at the end, the budget for maintenance and repair is quite limited. We don't have infinite budget to repair all the segments annually. Therefore, we have to consider the budget limits. To do that, we defined and we developed a new approach combining pavement management system models, PMS, and pavement lifecycle assessment using big data analytics and machine learning to assess this investigation. To do that, the first stage within our approach started from extracting the state-level pavement statistics from national databases, and then we went through the input contextualization related to collecting the data related to, for example, the ambient conditions, the climate conditions, as well as the thicknesses and the local maintenance and repair strategies. And then for each individual segments that we have investigated, we incorporated life cycle assessments to calculate the GHG emissions of the construction, use, maintenance and repair, and end-of-life impacts for different road types. And after doing the life cycle assessment, we conducted the regional and nationwide aggregation. One important point is that to assess this life cycle assessment, we need to consider the projected improvements in the future, not to overestimate the assumptions. Some of the policies and some of the already implemented solutions, such as vehicle fuel efficiency or the construction material impact reduction, have been already legislated and well forecasted in different databases. So for our projected scenarios that I will discuss later, we have already considered these solutions not to overestimate the savings and the environmental impacts in the future. So here is the result that we both incorporated the historical and the projected and the predicted results that we expect up to 2050. Here on this chart, you can see the annual GHG emissions of the pavement network in the United States, million ton CO2 equivalent, and on the x-axis, you can see the years. First, we start with the embodied impact. The impact associated with the construction materials is in order of 10 to 20 million tons annually. And we have the deflection-induced fuel consumptions, the excess fuel consumptions induced by the pavement rigidity properties, which is in the same order of the embodied impacts in the United States. However, the roughness, the smoothness of the surface can induce as twice as the embodied or deflection-induced fuel consumption in the total and contribute to the total GHG emissions of the pavement network. On the other side, we have the carbon uptake during the use phase, which is quite negligible compared to the other life cycle components that I discussed here. This is negligible because we don't have that much mileages of concrete pavements. Therefore, there is not enough exposed surface area to have carbon uptake. And we have the albedo effect, which is slightly larger than the embodied impact, both historically and in the future. So if we sum them up all together, you can see this black curve here, which is the total life cycle GHG emissions of the pavement network in the United States. And what is important to notice here is that after 2016, we have a decreasing trend in the total GHG emissions of pavements, but somewhere around 2038, we have an increasing trend. And when we look at the calculations and the mechanisms behind that, we will observe that the fuel efficiency of the vehicle predicted in the future is going to stay in a steady state after 2038, while the yellow curve on the right chart will have an increase for vehicle mile travel, VMTs. Therefore, the increase in the traffic volume will dominate the environmental impact rather than the offset that we get from the fuel efficiency. Therefore, we have to make an action to avoid this increase in the life cycle GHG emissions of the pavements. And it should be done in a faster way because the payback for concrete for asphalt and concrete is quite longer than the other types of infrastructure and industries. So to do that, we define a set of ambitious actions, so-called here, which is attributed to some of the pavement life cycle components. Some of them has negative, some of them has positive impact on the pavement life cycle component emissions. For example, one of the ambitious actions that we define is achieving net zero GHG mixture for both for asphalt and concrete in 2050. So the green arrow here shows that it has a positive impact, meaning that we have some savings for materials production and construction, while including concrete overlay to the treatment actions of high volume traffic roads in different regions may have negative impacts, meaning that some excess GHG emissions for materials and production, but we expect some savings for roughness or deflection-induced excess fuel consumption, the albedo radiative forcing because of the lighter color or the carbonation. And extending the end-of-life carbon uptake, meaning that if we leave the demolished concrete at the end of life for a longer time in the stockpiling site, we may give this opportunity to have more carbonation at the end of life. And the other ambitious action is increasing the budget, simply spending more money to repair our roads and have a smoother surface for the roads. Therefore, we have less excess fuel consumption, but on the other side, we will use more materials to do these actions. We have increasing the stiffness of the pavements to reduce the deflection-induced excess fuel consumptions, but we have to use some of the materials such as fibers or changing the binder type, which may have negative effect on the materials production. And at the end, the sixth strategy is increasing the surface reflectivity, which is painting the roads with lighter color that you can see in some cities in the US that will have albedo radiative forcing effect. And on the other side, we have to, for example, spend some material for some materials to paint those roads or change the binder type, for example, in concrete mixtures. So here is the results and the reductions that we could expect from all these solutions. It is the cumulative results from 2017 till 2050 for the US road networks for this analysis period. The y-axis shows the GHG emissions, the cumulative GHG emissions, and the x-axis, the first column and the last column, shows the no change and the ambitious scenario total impacts. No change scenario means that if we don't make any changes from what we have already implemented in 2016, and if we continue till 2050. So you can see on this graph that we have around 3.4 gigatons of GHG emissions during this period. 30% of this GHG emissions coming from the embodied part. Rest of them is attributed to the use phase, in showing the importance of the pavement, considering the total pavement life cycle in our assumptions and in our calculations. Most of them comes from the roughness-induced excess fuel consumption. And on the other hand, we have some dark purple solutions related to our ambitious actions and projected actions. Those already included in the policies, for example, fuel efficiency or some of the materials, improvements and replacements of recycled content. But all in all, we can see that we could reduce almost 65% of the GHG lifecycle GHG emissions of the pavement network, which is equivalent to 5% of the total road transport emissions during this analysis period. And we can see that while we could effectively reduce the embodied impact contribution to 16% in our ambitious scenario, the roughness is still important, and we may need to invest more to reduce the roughness-induced fuel consumptions and have a smoother road surface. Let's talk about the cost, which is the abatement cost. On y-axis, you can see the GHG abatement cost in terms of dollar per ton CO2 savings that we can expect from all these levers and attributes. And on the x-axis, you can see the total savings that I could show you. The deltas between two columns are 1.35 gigatons during this analysis period from 2017 to 2050. So starting from the left part, you can see that the low-hanging fruits, those solutions that have negative abatement costs, are those that are related to embodied impacts. In other words, for some of these solutions, if we implement them correctly, we both save money and GHG emissions. For example, low carbon binders, reclaimed asphalt, binder intensity, and optimization and reuse of pavement materials. On the other hand, we have a bigger opportunity to save GHG emissions in the use phase components, attributes such as reflectivity, fuel efficiency, stiffness. Therefore, it's a kind of trade-off to start from a low cost, and then we have bigger opportunity to start from the other, which has an abatement cost in order of $50 or $60 per ton CO2 in the future. So to conclude, first, we found that we have an increasing trend after 2038 for the pavement lifecycle GHG emissions in the United States. And we can effectively reduce the GHG emissions, the lifecycle GHG emissions during this period using the embodied carbon attributes and the budget increase. And the embodied solutions owe the lowest abatement cost, while the use phase solutions have the largest saving potential comparatively. And the proposed solutions is big enough to offset 5% of the U.S. road transportation emissions, the largest contributor to the U.S. GHG emissions. And in the future, we would like to have a disaggregated assessment and prioritize these strategies for different locations and different states, depending on the climate conditions that they have and the local maintenance and repair strategies that they have, to give them the best solutions and a guideline where to start this evaluation. With that, I would like to thank you so much for joining this presentation, and I'd be happy to take any questions.
Thank you so much for your presentation, and obviously you've done such a thorough review. So again, I'd just ask any of you if you're interested in joining us on the podium, or you can also join us and ask questions in the chat as well. And I can get us started off. You know, one of the things that I found really interesting was that you went from the state level, right? And then you went down to kind of what you said the network level was. Can you talk a little bit about the disparities of the data that you had across the different states, and how you kind of accounted for that in your really extensive model? Sure.
So one of the similar to other studies in this field and having this large scope of analysis for the whole United States was the data collection. And for some part of that, we have this opportunity to use the governmental data sources, which are consistently and homogeneously collected. For example, for the road mileages, the surface conditions, and the road geometries, we could have access. The data related to these parameters are publicly available in Federal Highway Administration websites. Some other difficulties that we have that we could overcome using data analytics and machine learning approaches to infer the data related to the thickness and some of the parameters related to the deterioration rates. Thanks to the mix of expertise that we have at Concrete Sustainability Hub in our research center, we could deal with that issue too. So what I would say is that most of the input data that we could collect was homogeneous, coming from one or two governmental sources. Long-term pavement program plan. This is another data source that historically collects the maintenance and repair actions happen to some of the specific road segments in different states and even in Canada. So this is another data source that we used for collecting the information related to the maintenance and repair actions and the types and the materials that they have used. NAPA, National Asphalt Pavement Association, is another source to understand the mixed designs of asphalt pavements, how much recycled reclaimed asphalt wrap has been already incorporated in those locations and in those states. National Ready Mix Concrete Association is another source that we use for example, concrete pavements to collect the data. So these are some sources, but we have a preprint of this publication. This work is already available, and we can have access to that as well.
Congratulations on the future publication. And it looks like Peter has a question for you.
Oh, please go ahead. Hi, Peter. I cannot hear you. I guess you're muted.
Sorry, how about now?
Yes.
I had two mute buttons to push. Apologies. How are you, Hessam? Good to see you.
Good to see you. Thank you.
I had two questions. One was, well, I guess the first was just about, you showed that cumulative total from 2017 to 2050 of greenhouse gas emissions associated with pavements in the US. What do you have a sense of how much that contributes to like overall US emissions? Like how big of a contributor is the pavement sector?
Sure. We compared this result, assuming the same the same set of assumptions, for example, for road transportation systems in the United States. So the tailpipe emissions, more specifically, coming from the vehicles. And we found that the total savings would be as big as 5% of the total transportation GHG emissions.
Nice. Okay. Thank you. And then a second question was around, you showed that what was driving the increase after 2038 or whatever was predominantly a function of vehicle miles traveled.
Sure.
Is that right? Okay. And what was the assumption there? I mean, is the assumption that vehicle miles traveled will just increase as there's no intervention, that we might actually drive less or shift to other modes of transport? Or like what went into that factor being the predominant driver?
Sure. So again, fortunately, there are some publicly available data on USEIA website and FHWA website that shows off some of these projections. For example, the future projections for both the heavy vehicles and light vehicles in the future, the improvement in the car fuel efficiencies and heavy vehicle fuel efficiency, as well as the electrifications. So these are some of the assumptions that we could adopt from those governmental sources.
Got it. Yeah, it would be interesting to see, if you ran like a best case scenario, maybe everybody switch to commuting by transit on a train or something, and exactly. To see how that would affect the pavement system. But
absolutely.
Very good. Thank you so much for humoring.
Thanks for your question.
Okay, everyone. This actually concludes this session. So the good news is if you're on the East Coast, you can get some dinner or go for a walk. I would like to call your attention to the keynote tomorrow, Mike Chester's going to be speaking in the morning. And even though this theme has ended for the day, he will be continuing with some of these ideas in his talk tomorrow. And then, as Jeremy mentioned earlier, just a reminder that we do have a really great opportunity to see a video on that is being sponsored, I think, by Amy Landis and some of the folks that have worked with her. So please make sure you can join that session too. And thank you so much to our wonderful speakers, and also to Beth and to Ron for helping us today. And that's it. See you later.
Thank you so much for joining us, and thank you for the organization.
Yeah.